Mate for that one. So for next week, we have 3 sections. So we have 6.1, which actually isn't a new section. So this one we read at the very beginning of the semester. So this was about factoring and x-intercepts. And so for the perusal reading, you don't have to put in new comments unless you come up with new questions, but I do recommend at least reading through it again, just because it's really nice to see how much we've learned and how far we've come. And then maybe also you can get a deeper understanding or pick up on some subtleties that you didn't notice the first time around. So I do recommend rereading it, but you don't have to comment on it. 6.2 is about quadratic equations, solving quadratic equations, which we've been doing for a long time and even beyond quadratic equations. But this section introduces 2 new techniques. So with the techniques we've been using so far, with factoring and the different kinds of factoring, sometimes there are equations that we can solve, but we can't factor them. And so this gives us 2 techniques. So 2 techniques that work in these other situations. One of them is called completing the square. And the other one is the quadratic formula. So these are both just 2 techniques that solve the same problem as factoring. So this like solves the same problem as factoring. As factoring. So it gives us the roots of the equations, when the expression is equal to 0, it gives us the roots, but it works in some cases when factoring, when we can't factor. It works in some cases when we can't factor. So it's factoring, especially for like simpler quadratic equations, factoring is often like a little easier and faster, but the quadratic formula will just always work. So if you're like, I just don't want to try, you can always like plug it into the quadratic formula. It'll give you the solutions. If your goal is to factor, then you have to like translate the solutions back to a factored form, which is also possible, but sometimes can be a little bit trickier. Okay, so we have those 2 sections, and then we have 6.5, which is on inequalities. Inequalities. And so this is, a lot of people find this topic very challenging. It's, so far we had like expressions that we were simplifying, and then we had equations where you have an equal sign and you're like, okay, I'm comparing these 2 things. I can do one thing to the equal sign, like my scale, as long as I'm doing the same thing to the other side. And we use those techniques, that idea, to solve equations. Inequalities means these are things where the 2 sides are not equal. You want to find the x values so that one side is either less than or bigger than the other side. So I want to sort of compare these 2 things. Let's do this. So we have solving equations, which is what we've been doing, versus solving inequalities. So solving equations. So let's just look at an example, something that we're very familiar with by now. So for example, x squared minus 4 equals 0. So this is an equation with an equal sign, and we know how to handle this, right? So we can factor the left side. We have x minus 2 and x plus 2 equals 0. And then we have the 0 factor principle. When you're multiplying 2 things and you get 0, that means one of them has to be 0. So either x minus 2 equals 0 or x plus 2 is equal to 0. So we get x equals 2 or x equals minus 2. So this should be very similar, very familiar to you. And we get exactly 2 solutions. Right. And what that means is these 2 values, x equals 2 and x equals minus 2, are values that when I plug it into the left side, 2 squared is 4 minus 4 equals 0, I get the same thing as the right side. And those are the only two solutions, right? So that's it, everything you can do, right? When we do solving inequalities, so for example, we have x squared minus 4 is bigger than 0. So now we're looking for the x values, not where we get equal to 0 when we plug it in, but the x values where you get something that's bigger than 0. Here we have not just two answers, we have infinitely many solutions. I'll put this in orange to compare. As infinitely many solutions. And some of them you can just see, right? So for example, x equals 3, right? If I have 3 squared, 9 minus 4 is 5 is bigger than 0, or 4, or 5, or 6, or 7, or 8, or 9, or 10, right? I can go on forever. I also have things like minus 3, right? Because I square it. 9 minus 4 is still 5, it's still positive. Minus 4, minus 5, minus 6. I can go on forever and ever and ever. They don't have to be integers, right? So something like pi is a number that's bigger than 3. I square it, it's definitely bigger than 4. You can find out, which is, I subtract and get 0. It's something that's positive. So I can get a fraction like 17 over 2. I can get something like square root of 17, right? There are infinitely many answers to this inequality, not just 2. And that means that we're going to be expressing our solutions with interval notation, which I know everyone loves. So if we want to, we're going to come back to how to solve this thing algebraically. If we look, for example, another sort of example, at x squared minus 4 less than 0. So now I want any x value that I plug in that makes the left side negative. This also has infinitely many solutions. Infinitely many solutions, infinitely many x values that I can plug in that when I square it and subtract 4, I'm going to get something negative. So for example, x equals 0, x equals 1, x equals minus 1, x equals 1/2, 1/3, 1/4, 5 over 6, whatever, minus pi over 2. I can go on and on and on and on. There are infinitely many numbers that make this negative. So we have lots and lots and lots and lots of solutions. We can solve both these things, the equation and the inequality, graphically, if you know what it looks like. And fortunately, with our transformations of graphs, we know exactly what this, this function will look like. So we can solve these, solve graphically. So what do we want to do? We want to draw the graph of y equals x squared minus 4, which we know how to do. X squared is our basic parabola, U-shaped, and minus 4 means that we've shifted down vertically by 4 units. Minus 1, minus 2, minus 3, minus 4. So the bottom of our U is down here at 0, minus 4. Excuse me, oops, positive 1, minus 1. So, right, we've just shifted our graph down by 4 exactly. So that means that our, maybe I should do this in a different color. Our next points on the graph will be up here. Our 2 and minus 2 should be 4 units up from the bottom. So that's where we're going to hit the x-axis, and then we get this U-shaped parabola like this. So this is y equals x squared minus 4. And so if we want to solve this for, solve x squared minus 4 equals 0, that's where the y value is equal to 0. So that's exactly at these points, x equals plus 2 and x equals minus 2. Those 2 points are there. And if we want to solve, on the other hand, for example, x squared minus 4 is bigger than 0. So we're looking for where the y values are bigger than 0. So that's everything here on up. And we have an open circle like this. And so we see that the x values are going to be minus infinity to minus 2, union 2 to positive infinity. And similarly, if we wanted to solve x squared minus 4 less than 0, we would take the negative numbers down here. We can also solve this inequality algebraically. So we can also solve the inequality x squared minus 4 greater than 0 algebraically. So we have x squared minus 4 is bigger than 0. And what we would do is the first thing you're going to do is actually start out the same way you would solve the equation. So we can factor it, we can find the zeros where x squared minus 4 is equal to 0, and you would do the same thing. You can factor the difference of two squares, and we get x equals 2 and x equals minus 2. And the reason we want to find the zeros is because if you think about it, if we have a nice thing like a polynomial, the only place where your graph can switch from positive to negative or negative to positive is where it goes through 0. So if we find that it's equal to 0, then we can say, okay, well, everything on either side of that has to be either positive or negative. It could bounce back off and be positive on both sides, but it can't possibly just like switch from positive to negative if it doesn't go through 0, if it's a nice continuous connected graph. So what we do in the next thing is we set up a number line. We do something called sign analysis, where we set up a number line and we mark off the places where we know our function is equal to 0, x equals 2, and x equals minus 2. And those are the only places where our function y equals x squared minus 4, it's equal to 0 at those two places. And those are the only places where it can switch from positive to negative or negative to positive. And so what you can do is just test a single point in between or on the other sides. So test a value here. Anything that's, oops, I put them in the wrong way. This should be minus. And this one should be plus. So I want to test any x value at all that's less than minus 2. So test, for example, x equals minus 3. In between here, I can test anything at all. I'll probably test x equals 0 because it's easiest. And then I have to test something that's bigger than 2. So test x equals 3. And what you're doing is you're saying, okay, if I plug in 0, and it gives me a negative number, that means all the numbers between minus 2 and 2 are going to be negative. If I plug in 0 and it gave me a positive number, that would mean all the numbers between minus 2 and 2 are going to give me a positive number because it can't switch anywhere except where it's 0. So we just test x equals minus 3. So we're like, okay, minus 3 squared minus 4, that's 5, and that's positive. We test 0. That's minus 4, and that's negative. We test 3, that's 5, and that's positive. And so if we're trying to solve, always remember what the question is, x squared minus 4 is positive. So that means x squared minus 4 is positive for x in the interval minus infinity up to minus 2, union 2 to positive infinity. If we wanted instead, very similar, if instead we had the inequality x squared minus 4 is greater than or equal to 0, what would our solution be? How would it change? Mason, you have an idea?
Well, to start, the notation would be different because the points would be inclusive rather than being non-inclusive.
So what would you write down for your solution instead?
So for x in negative infinity to -2, or sorry, -4, or sorry, yeah, -2 inclusive. So like a hard bracket, and then union to another hard bracket to positive.
Great, exactly. Right, so if we're looking for all the numbers where we can plug in x and get something that's positive or equal to 0, we have all the same numbers, anything that's less than -2 or anything that's bigger than 2, but we can also include -2 and 2 because those ones make it equal to 0. So we would get a slightly different answer over here. We're going to leave it at that today. So excellent work, everybody. We have 4 new outcomes coming on to the Friday assessment this week. So solving exponential equations, rewriting our log expressions using the log laws, and then compound interest and exponential growth or decay. So you can study for those. If you're not ready for them yet, it's okay to be like, okay, I'm going to work on some other outcomes, the old ones first, and get there. And if you need help sort of strategizing or something, feel free to come in and talk to me and we can work out a plan for you. Okay, so